Right, part two. Yeah, what started me thinking about this Big Bang thing again was hearing about the expectations of what we would see with the James Webb Telescope, i.e., the early universe. So, what follows, I think, reinforces my previous argument by showing that this expansion model is incoherent and it's the product of wrong-headed, muddled thinking. Okay, because light has a finite velocity, we see distant stars as they were a long time ago, when their light was emitted. With the James Webb, we can see detail of galaxies and stars further away than ever before, and therefore older. Now they've calculated that the Big Bang happened about 13.8 billion years ago. To get this, they used distance and velocity measurements, basically obtained a constant, and that the constant describing the accelerated motion of stars away from us. It's a so-called lambda CDM model. So that's from that they calculated the elapsed time since the beginning, since the distance was zero. Right, the initial expansion went through several stages, and then they think, and then as things cooled down, stars began to form. Then through gravity, began to cluster together to form galaxies. It seems that they expected that with the James Webb we'd be able to see detail of an early period before large galaxies had formed. Right, so I've done a time distance graph. With a vertical axis of time and horizontal is distance. So remembering that we are at the centre of this expanding universe, as is everywhere. All points are at the centre, so the graph can be centred on us. So as we view stars with their old light as it comes to us, the light by which we see them travels along this line. So all the light from all the stars we see now is represented by that line. Okay. So the gradient of that line represents the velocity of light. Okay. And then I've drawn that line to represent the velocity of light going in the opposite direction from the beginning of time. Okay. So, for instance, we've got two stars there, So we're seeing this one as it was about 4 billion light years ago, 4 billion years ago, and that one about 2.5 billion years ago, okay? See there, the slightly curved lines, that's their trajectories, they accelerate away from us, okay? So because of its acceleration, you can see that that star now is, its velocity is approaching the speed of light, okay, away from us. Let's turn over the page. The point is that if we accept this representation, all the stars and galaxies that we can see would have been moving away from the Big Bang origin for a long time, and therefore they'll be old. For us to see very young stars which formed very early, they would have had to get right out here. So that the light that we see them by could be arriving at Earth now. But this area of the graph obviously is outside the expansion, so if you accept this representation, there's no way we can see the early universe. For us to see stars from the early universe, they would have had to get out here very quickly, at multiple the speed of light. Okay, so obviously that there must be a different way of representing the expansion. Right, so think again of this tiny seed that was to become the everything and everywhere of our universe, okay? So what if there was, within that little tiny point, what if there was an inherent separation of locations, of huge distances, but on a tiny scale? As the expansion began, there would already be separation of billions of light years between points of the early universe. So, for example, there would be locations 13 billion light years from us, and any light generated then would take 13 billion years to reach us. As the expansion continued and the fabric of space was stretched, the scale of distances would increase. So I've tried to represent that in another diagram with an expanding distance scale. Okay. So, if you like, you think that is already contained within the Big Bang before it actually begins expansion. So the scale starts off very small and gets larger. So I've got two youngish stars there, and they began emitting light, and that is the track of the light as it travels towards us, with initially a very steep gradient because of the small scale, the gradient increasing until when the light reaches us, at our local scale, it matches our local speed of light. Okay, yeah, two young stars are changing. Yeah, I mean, this scale change could possibly be a combination of an expanding distance scale and a changing in the time scale as well. I mean, space-time is supposed to be curved, space-time, so maybe both time and distance scales have varied. Okay. But however you drew this diagram, it would be 300,000 kilometers per second towards us in per second. Okay. Yeah, curved space-time. Just a little aside, I found this account on Wikipedia. So I presume it's a correct representation of what it's supposed to be about. Yeah, 13.8 billion light years. This is the distance, quote, this is the distance that a photon emitted shortly after the Big Bang, such as from the cosmic microwave background, has travelled to reach observers on Earth. Because space-time is curved, corresponding to the expansion of space, this distance does not correspond to the true distance at any moment in time. Now that's not 100% clear to me what he means there. Anyway, this is obviously a clever guy, a professor or whatever, so he maybe thought it was just too obvious to go into detail. He didn't really need to spell it out. So okay, so this model sort of works then. However, what does this model require? Well, the starting point of the Big Bang Theory, as we saw in my previous video, has everything at the centre, which was necessary to explain the equality of redshift in all directions. Okay. But this model, which I've tried to explain why they might have thought that we could see the early universe, requires an inherent separation of huge distances inside this nascent universe, so that matter can be far enough away from us immediately, as I've shown in that model, so that its radiation will take billions of years to get back to us. So is that reasonable? You know, that every point in the universe is central, but then that there is a huge separation of points. I don't think so. Secondly, presumably the universe will continue to expand for many more billions of years. So future observers will continue to receive radiation from the early universe. Why wouldn't they? So doesn't that mean that the inherent separation would have to be extremely large, if not infinite? Or do they think there's a limit to that size? Was there a finite amount of matter that will, so that one day there won't be any more? Yeah, it's hard to get your head around that. Thirdly, the distance scale is stretching. In fact, how they like to phrase it is the whole fabric of space is getting larger in 3 dimensions, remember. So if you visualize a 3-dimensional stretching and enlarging, the stars themselves presumably are getting bigger, won't they be? So are they retaining their density? So if there were, that would mean the mass is increasing, is it? And of course, we've still got the old problem of the equivalence of viewpoints. Because an observer at a receding star, receding from us, he would presumably be able to look back at us and expect that it is us, that we're the ones who are being stretched and enlarged as we move away from him. So it's another twins paradox type deal. Now lastly, and I think you'll love this one. Redshift, okay. This model implies that stars are fixed in position and their movement is due to the stretching of the fabric of space-time. Now this is a different concept to that previously discussed in the first video, in which stars move relative to a fixed space, which causes that stretching of the light and hence redshift. Yeah. If you remember this diagram, yeah. The star moving away from us with velocity v, so the light is stretched, so the absorption line is at a longer wavelength, okay? But in this model we've just been talking about now, it's the scale that is stretched. So wavelengths are going to retain their lengths relative to their local scale. Would they? Yeah. So surely that would mean that when the light reaches us, absorption lines would be at the same position as they are in our local light. Because both the light from our sun and the light from the receding star are both now moving in our local scale. Okay. Show that in the diagram. So there you've got the expanding scale out to the receding star, but as the light comes back towards us, the absorption line there, okay, in the middle. As the light approaches us, the scale is reducing to become our local scale, and the absorption line, when it gets within our environment, is at the same, will it be at the same wavelength as it is in our light from the sun? I reckon so. No red shift. So I've tried to construct a model that would justify their belief that we would see the early universe, and to my mind it just falls apart when you start to examine it. Anyway, the results from the what we're actually seeing through the James Webb, we're not seeing an early universe, so I think that puts the lid on it, really. And I've said before, it's the psychology of all this that intrigues me most. An example of that, a word about dark energy. We start off with the creation of a huge, maybe limitless amount of stuff emerging from nowhere, flying apart with accelerated motion. Now that's a totally alien concept, totally at odds with our experience, okay? Then to this has been added another alien concept, a force, dark energy, which is supposedly driving this expansion. This energy being created in ever greater quantity from nothing, from nowhere. Okay? So did they think that this idea of dark energy gives the whole concept of the Big Bang legitimacy? Because that we're used to if things move, some things move them. You know that we can understand that. So it just seems irrational to me that they believe that adding dark energy to the mix means it gives it legitimacy and we can understand it. We can't. It's just adding, it's compounding a fantasy. Yeah. If you get my drift. And it's interesting to look at how the Big Bang usurped the steady state and static universe theories and became accepted by the community of cosmologists. They cite all the supporting evidence, knowing that there's a lot of very strong evidence that contradicts. I'll talk about that in another video, I think. Remember, confirmation bias. It's a real danger. And anyway, no amount of evidence can validate an impossible, nonsensical theory. Is there an element of heart ruling head? The Big Bang, it's got great aesthetic appeal. It's a good story. It's got a beginning, it develops, and then the ending, it's like an open-ended mystery of possible endings. And it's Earth-centric. In fact, I could say it's egocentric. Because I'm at the centre of my universe. I'm a point in the expanding universe, and we're all inherently central. Egocentric. Well, it's a thought, isn't it? So has this appeal, you think, caused a mass blindness to the logical inconsistencies? Or is it simply an intellectual deficiency in the capacity for logical analysis, inability to visualise how a 4D model would work? I find that hard to believe, but that they've got some neural pathways up there which are not connected properly. There's a cynical view. The Big Bang provides like an open-ended requirement for more detailed measurements, refinement, more research, more discussion, more fun in general. Whereas a static universe, for example, in comparison, has got limited potential and it's a bit of a bore. A lot less glamorous. There's quite a few celebrity physicists out there who seem to enjoy this sort of guru philosopher status. There must have been a lot of dissenters. Did they decide it was expedient just go along with the consensus, the groupthink? So what's really going on out there? Well, it looks to me like a static universe with redshift due to the loss of energy / velocity of radiation. but beyond that, who knows? We're not equipped to understand the very large, or the very small for that matter, the subatomic. I mean, studying these areas, it's not completely pointless, as long as we just acknowledge that we're never going to understand. Okay, that's about it. I'm going to do another video, sort of an addendum, to make some suggestions how we could reinterpret observational evidence if we allow the possibility that radiation loses energy, hence causing lengthening wavelength and or reduced velocity. Okay, thanks for watching. See you next time, hopefully.